Hello everyone. Today we will be solving a problem from Geometric Inequalities. This problem is from the famous book written by Bottema named Geometric Inequalities. You can try out that book to learn more about geometric inequalities and its approaches. And let's consider a triangle with side lengths ABC. Let capital R denote the circumradius of the triangle, that is the radius of circumcircle, and small r denote the inradius of the triangle, that is radius of the inscribed circle, and we have small s that denotes the semiperimeter of the triangle, that is half of the perimeter of the triangle. Now we have the equation or the inequality that needs to be proved, which goes like a times s minus a plus b times s minus b plus c times s minus c needs to be proved less than or equal to 9 times capital R times small r. So this inequality is a bit weird because LHS is relating the sides, whereas RHS is relating the circumradius and inradius of the triangle. Now how come we can compare these two? So this directs you to represent the radii in terms of sides of the triangle. So first we will be doing that. And later on, we will be requiring Schur's inequality in order to proceed further. So we will learn it after converting the capital R and small r in terms of the side lengths of the triangle. And then you will see that the problem is quite trivial. So let's get started. So here is the equation that we are having, or the inequality: a times s minus a plus b times s minus b plus c times s minus c needs to be proved less than or equal to 9RR. All right. So let's approach this clearly. So first, the term 9RR in the RHS might seem to be absurd, but actually not. We can write it in terms of ABC. So how will you first simplify the expression for R, the small r in radius, is by the following. Consider the triangle that we have, and suppose if you have the incircle as shown. Incircle is the inscribed circle in the triangle. Now we have the in center I, and perpendiculars are dropped, which falls on the point of tangency to the circle. Let's construct the triangles BIC, CIA, and AIB. So the total area of this triangle, which is delta, can be represented as sum of these three areas, and the areas of these individual triangles would be half times height of the triangle, which is the inradius, times the base length, which is C. That corresponds to AIB's area, because AB is C, BC is A, and AC is B. So in a similar way, BIC would have the area half times R times A, and CIA would have the area half times R times B. Now this simplifies to just R into S. So hence, we get that small r is actually delta by S. All right, what is delta? Delta is the area. So let's try to write area in some other way. We know that area can be represented as half BC sin A. that is half times the adjacent sides multiplied by the sine value of the angle contained between those two sides. So by S, now sine A. What is sine A? We know sine rule, which states that small a, that is the side BC, equals 2 capital R sine A. This is quite simple to realize because on the circumcircle, we have the angle capital A and the length of BC can be determined by regarding it as a chord on the circumcircle. And we know length of chord is just 2r sine the angle it subtends. So it's 2r sine A. So going back here, we get half BC by S and sine A equals A by 2r. So thus, transforming the equation by moving the 4r in the denominator of RHS to the LHS, we get 4 capital R small r equals ABC by S. Beautiful, right? Because we have now represent the product of the two radii in terms of sides of the triangle. So thus, 9RR equals 9ABC by 4S. So writing it here, we get 9ABC by 4S, and hence it is just equivalent to proving that the left-hand side expression is less than or equal to 9ABC by 4S. Now let's try that. So the to prove statement thus simplifies to A times S minus A plus B times S minus B plus C times S minus C less than or equal to 9ABC by 4S, and recall that S equals A plus B plus C by 2. So now we have the entire expression in terms of just the side length of the triangle. So now we have to invoke certain useful properties of inequalities in general. Schur's inequality is one of the nuanced inequality in the subject. So let us mention that because we have its direct application here. So Schur's inequality. It talks about three positive real numbers. Let ABC be three positive real numbers. So you have to exclude 0 as well. And lambda be any real number. Then we have the following. A per lambda times A minus B into A minus C plus B per lambda into B minus A into B minus C plus C per lambda into C minus B into C minus A is always greater than or equal to 0. It's always greater than or equal to 0. Equality holds. So you must learn inequalities along with its equality condition. So equality holds if and only if A equals B equals C. In no other circumstance shall it hold true. All right. So we will not be proving this, but the proof is quite simple. You can take that as your homework and write your ideas in the comments. But we will directly use this particular result in order to arrive at the conclusion shown above. So how am I going to use it? For this, I will just copy the statement and simplify it in the following way. So here is our statement. Let's just expand it. It might seem brute force, but we will be able to easily arrive at the result. We can just take the S to the LHS and we get AS square plus bs square plus cs square minus a squared s minus b squared s minus c squared s is less than or equal to 9abc by 4. We can also take the 4 to the LHS and we get 4 times of s squared. So that is just a plus b plus c the whole square by 4 times a plus b plus c minus 4 times of s, which would be a plus b plus c by 2 times of a square plus b square plus c square is less than or equal to 9abc. Alright, so simplifying this, 4 and 4 gets cancelled, and let's take the a plus b plus c outside, and we would get a plus b plus c times of a square plus b square plus c square plus 2ab plus 2bc plus 2ca. That would be the expansion of a plus b plus c whole square. And we will be subtracting a square plus b square plus c square times of 2 from it. And we would end up with 2 times of ab plus 2bc plus 2ca minus a squared minus b squared minus c squared. This is the LHS. So let's just keep on expanding the LHS and see what happens. When you expand this one, you would get 2a square b plus 2abc plus 2a square c plus 2b squared a plus 2b square c plus 2abc plus 2abc plus 2bc square plus 2ac square minus you would get a cube minus b cube minus c cube and then minus ab square minus ac square minus ba square minus bc square minus ca square minus cb square to be less than or equal to 9abc. So this is our to prove statement. So upon simplifying, you can get that a square b plus a square c plus b square a plus b square c plus c square a plus c square b is less than or equal to a cube plus b cube plus c cube. And in the LHS you have 6 ABC, in the RHS you have 9 ABC. The resultant would be 3 ABC. So now this is in some symmetric form. It's good and it's also eye-pleasing. So if you shift the terms to the RHS, you would get a cube plus b cube plus c cube minus a square b minus a square c. And let's take a common. So if you take a common from these two, you would get a times of a minus b times a minus c. Or in other words, you would get a square minus ab minus ac plus bc. And this is with these terms. And you have a plus ABC. Similarly, group the other terms, b cube minus b squared a minus b squared c plus abc. So this can be written in the form b times b squared minus bc minus ba plus ac. And the other term similarly is greater than or equal to 0. This is what we have to prove. But notice that these terms in the bracket just simplify to a minus b into a minus c. plus b times b minus c into b minus a plus c times c minus a into c minus b is greater than or equal to 0. So you could say that this turns out nicely to be in the form of Schur's inequality when lambda equals 1. So that is, with the power of 1, the 2-pro statement is nothing but the Schur's inequality, hence we can be sure that it is true. So maybe the way we proceeded seem inflated, but these factorizations and everything would be trivial when you are able to recognize this form as the Schur's inequality. So explore much more inequalities in the book that we had mentioned. I hope you enjoyed this solution. The notes of it will be provided in the description. Let's meet in the next video. Happy learning. Bye.